Lecture 23, GPU Programming Continued. Alright, we learned a little bit already about how a kernel works, how you write one, how you compile one, well, even how to do it well. But what we haven't yet covered is the host code stuff, we're going to have to talk about that now. The good news is that although we have to write our host code we have to write our kernel code in a C++-ish language, actually you can write your host code in Rust. We're just going to use a particular library for this, the Rustacuda library. That's linked in the notes as well, and it is a fairly simple library that is straightforward and does exactly what we need and nothing super fancy. The goal is to limit our interactions with unsafe code. We want to do, obviously not the important work of the kernel, but we want to do all of our setup and everything and minimize the amount of the code that is going to be unsafe. There will inevitably be some unsafe component because, we're going to have to interact with the kernel, and that is inherently unsafe, but we'll try to keep it as small as possible. Okay, so we're going to first look here at a very simple kernel from the Rustacuda examples. The goal is not to do anything particularly useful. It is just about getting us to say, we've launched a kernel. Straightforward, no magic, no nothing. We'll return after this to the n-body host code. As you saw, if you watched the previous segment, we have it. It works. So let's take a look at it. But in any case, as before, we're going to include a prelude because that seems to be fairly common. That's something that we need. All right. One thing I want to point out that you won't find in here is an explicit call to initialize the runtime. That is a clear distinction from, say, if you've done this in C or C++, where you have to explicitly initialize it. Because this is Rust, not necessary, we can skip it. The CUDA runtime is automatically initialized when there's the first call into it. Therefore, you may encounter an error from a call that you wouldn't expect. When we're trying to get started, you might see something that, why would that happen here? It's because it's the first time you're trying to use the CUDA runtime, and for whatever reason it may not be configured correctly, in which case you encounter an error in the beginning. Okay, let's begin. So we've included the prelude just as we do for Rayon. It imports a bunch of commonly used types, and putting the star on there just reduces the amount of import statements that we need. Your code style may allow or forbid the use of star. Our main function now returns a result, which under normal circumstances returns nothing, but could return an error if something goes wrong. That may be helpful if you want to look at it. And our first step is Rustacuda init. So we're going to initialize the API, and it has to happen at the start of the program, so there's no sense in initializing it anytime later. Just don't delay, get started now. At present, there are no flags at all, so the CUDA flags empty operation is the only valid argument to the initialization function. Okay, sure. You could have made a default constructor, but I'm not the maintainer of the library, so there's that. And then we have to get a device. And a device is your graphics card or any other hardware that potentially does the work. It's possible that you have more than one compute device in your system, in which case you wouldn't want to have get device, just take 0 as an argument. You'd want to get all of the devices, but here we'll have only one, and we'll just take the first one. The third step is a context. And the context is described by the CUDA documents as being analogous to a process. So when we launch something within a context, it executes within that context, it has its own address space, and when the context is destroyed, all its resources are cleaned up. Each host thread may have one context, and the call here is create and push because a host thread has a stack of current contexts. it turns out we don't actually need to use the context for anything. You'll notice that the CTX there is prefixed with a little underscore, which just turns off the warning from Rust. The compiler will tell you, hey, this variable is unused. Why create it? Well, the thing is, we don't need it for any later step, but we have to be in possession of one to use this stuff later. If the context gets dropped, that cleans up things that we need to run the rest of our code, and that's not going to work. So we don't want that. We need to keep the context around. In this simple example, it stays in scope because everything happens in main. If you are going to have more structure in your program, if you have an init CUDA function, you need to give the context back to make sure it doesn't go out of scope and get dropped, because it has to exist. And without it, other functions don't work. When it does get dropped, of course, then your standard cleanup options take place. So in this case, create and push takes a couple of arguments. Map host and automatic scheduling, we're fine with those, as well as the device that we got in our previous step. Next, after that, you'll see we are going to read in the compiled PTX file. This is not the one we made earlier with nbody. It's a different one, and I'll show you what the source code for the kernel looks like later. But we're going to read it in as a C string from the resources directory, and it's called add.ptx. So we've got that ready. And then we're going to create a module. And a module is technically a package of code and data to run on the device. That's a fancy way of saying it is the kernel. So we read the compiled PTX into a C string and say create the module from that string. You could also create a module directly from a file if you prefer that shortcut. Either one will work. Great. So we've created a module. And then we have to create a stream. And a stream is where we assign work. You can think of a stream as being similar to a priority queue. You put items in there, and work that is more important, which means it has a lower priority number, can preempt work that is less important. Otherwise, work is done in the order that it is scheduled, and tasks don't overlap. So this is an asynchronous operation. So when you put things in the stream, that returns immediately, and then they will eventually get picked up by the GPU and done. The Rust CUDA implementation says you should set the non-blocking flag when you're creating the stream to prevent synchronization with the null stream. I don't want to go into the details about that, really. Just use this with non-blocking as we should. Okay, that covers all of the generic setup that we were interested in doing, as well as loading the kernel that we want to execute. Then, when we are transferring data between the host, so your RAM, and the device, the GPU, we got to have some data to transfer. So, with the setup aside, we are going to now create some input and output buffers. We'll call them in-X, in-Y, out1, and out2. And these are going to be buffers where we put some data to send to the kernel, and where the kernel is going to write its data when we're done. For a real problem, creating these buffers might be more interesting than just creating buffers where it's 1 in the first buffer and of capacity 10, and 2 in the second buffer of capacity 10, and the rest is all zeros. But this is supposed to be a very simple example where we just transfer some stuff to the kernel and say, hey, kernel, could you do a little bit of work, and then get the result back. So create buffers for data should be a bit better. Remember that this is explicit communication. So whatever data that we have to explicitly put it into a device buffer. That's something that we can transfer over to the kernel. And then when we're done, explicitly get it out and transfer it back when we are done. So we have to wrap it a little bit in the device buffers here. Okay. Doing well so far. There we go. Then we are ready to go. We are ready to launch. And the kernel itself, a comment here that says that add each element in X and in Y and writes the result into out. And launch the kernel with one block of one thread, no dynamic shared memory, using the stream that we called just stream. And so this has to take place in an unsafe block. The launch macro is the one that says, GPU, we're ready for you to do some work. And we say let result equal launch macro with the module that we've created, .sum. That's the function that we want to execute. Some arguments to tell us about number of blocks and number of threads. And we say no dynamic shared memory. And then we specify as our arguments the input buffers, in X as device pointer, in Y as device pointer, out1 as device pointer, out1.length. So the unsafe block is really just launching and returning the result out of our code. And that's, well, it's easy to audit. You know, the area of extra scrutiny is fairly small. So we give our buffer and we use as device pointer on them. It's to go to the contents of the buffer, right? We're interested in the data that the buffer contains, remembering that, you know, things like the length property on a buffer are Rust niceties that the kernel cares nothing about. And so, you know, the slightly more complex data structure that represents a device buffer, we're not interested in its structure. We're not interested in anything else. All we really need are the contents, and that's what we are going to supply. For scalar types like the count, no conversion is necessary. We just provide the value, and we specified the grid and block size as 1 each. And after that, we have launched. We have sent the stuff over to the GPU, and the launch is asynchronous. So after the information has been transferred, we're done, and we actually call stream.synchronize to make sure we wait for the kernel to be finished executing. In principle, you could start something else or do something else in the meantime, but we don't have anything else to do here, so we can just launch. And then when we are done, the synchronization has completed, we copy the items out of the buffer. So again, we have to do a little copy operation here. So we have a new array, a new buffer where we're going to copy the data to. And that's it. We can then, here there's a little assertion to check that, you know, the math actually happened, and there's a print line that says the kernel launched successfully, and we end main with an OK, and that's it. We're done. It checks all the values are equal to 3, and that's the end. We have a simple working example of how to set up, launch, and collect results, collect the correct results from a CUDA computation. All right. Not too bad. But of course, you don't want to see that. You probably want to see the n-body host code. Okay, but before that, I'll show you the kernel. And this corresponding kernel shows you, incidentally, how to declare a constant in the CUDA-like C-like language, and it's just extern C constant. My constant equals 314. It's not needed for anything, but in case you were curious about how to do it, there you go. Here it is. After that, our sum function, you know, given x, well, you know, just take a look over our data and, you know, perform the addition, and that's it. That's all there is. Nothing real exciting there. There's a little bit of complexity in the, you know, for condition, because we are saying, well, if block index.x times block dimension x plus thread index.x, based on the way that we called it, block index and block dimensions are both going to be 1, so we don't really have anything interesting there. But that is intended for if you wanted to split it up a little bit, you would have to be more clever to make sure that you're iterating over the right elements in the array so that we know where to start and we know where to finish. So you could mostly ignore that. You could just say, oh, I is thread index.x, and go from there. All right, we launched one. This is a kernel. You would compile it with NVCC, and it would be ready to go. Right, finally, you want to look at the n-body code in the repo. Okay, we are ready to look at the n-body code. It is very similar to the example that we have just talked about as the standard stuff for creating and launching a kernel doesn't change at all, really, based on which kernel you want to launch. We are, however, going to point out some of the important differences. I mentioned earlier when we showed the kernel that does this calculation that we relied on the vector types that are built into CUDA, float3 and float4. Those are not natively supported in Rust, and they're not actually natively supported by the Rust CUDA library. Maybe by the time you were doing this, I will have found the time to actually add support for them to the library. I've been invited by the maintainer to submit a pull request, but I haven't had the time yet, and at the pace that things are going in the current term and to prepare for next term, I don't know that I will in time for everybody who's going to be watching this video. Maybe we'll see how it goes. So the vector types are actually imported from a different library. In this case, it's CUDA sys, which I have imported, and it brings in these types of float3 and float4, which we need, and I use them to replace the previous types I had for point and for acceleration, because we don't need them anymore. We'll treat them as float3s and float4s. And that will get the job done. We include our Rust CUDA prelude. We have our C string import, everything like that. Great, we're ready to go. We have 100,000 points, and we have our space measurement as F32 being 1,000. And then what have I got here? Yeah, this is part of the problem that I want to solve by making a contribution to the Rust CUDA library, again, if I can find the time. And it is that because the types are not sort of natively supported, I have to, well, hack it a little bit. So I declare a struct CUDA float4, which has as its component a float4. Why do I have to do this? Well, because I have to implement device copy for that type. And I can't do that on float4 because it's not my type and it doesn't belong to me, so I have to be a little bit careful about that. It is a requirement of the Rust CUDA library that any type that we want to send over to the kernel must have the trait device copy, and implementing that trait is promising that the type that you have does not contain any pointers to host memory. So if you had a struct that contained a pointer to a buffer or something, that would be not okay, because that pointer will not be valid when you are running on the GPU device, because they don't share memory. The memory address that it references is not valid. It's not one that the GPU can use, or if it is, it's not the data we're expecting it to be. So there's no requirement in terms of implementing it that I have to do anything, but it does require my explicit acknowledgement of the terms and conditions that, to implement this type, I have to say, well, I'm sure that there are no pointers in there that we're going to use. That's an easy promise for me to make when it's a float4. It is a float and a series of floats, and therefore there's really not anything I have to do. To make my life also a little bit easier and to make sort of the syntax slightly nicer, I also added the deref trait, making it so that an array of the type CUDA float4 will easily be converted to float4 when we operate on it. It's just a way of saying, and the deref trait is implemented on things like a mutex as well. It's just a way of saying that the type in question is really a container for something else, and sometimes you want to just go directly to the contents of the container as opposed to operate on the container. And so for that reason, I implement the deref trait for float3 and float4. If you're a Rust expert, you might be sad because basically I've done the same code 2 times, and this could be a macro, and then we could do it for float and float2 and float4 and float3 and int2 and int3. I know. This is just what is the quickest way that I can get this working, especially because, as we've discussed, I've planned and discussed with the maintainer of the Rust CUDA library that if possible, I will try to add these properly to the library so we don't have to do this anymore. Nothing to see here. Move along. All right, we're then going to look at main, and main does the initialization steps that we've talked about. Those are as we would expect, so we're going to init with flags empty, get device 0, create and push, and then we can initialize our positions as we did in the original problem, and we initialize our accelerations again as we did in the original problem, and we load the PTX that I showed you earlier and turn it into a module, and we create a new stream. Okay, and then to get ready to send the data in, we create device buffers from the slices of data that we saw before. You'll notice that accelerations is a vector of CUDA float 3 and initial positions is a vector of CUDA float 4. We can go down and look at those, but initialized positions, again, instead of returning points, it's now CUDA float 4, and because of the way that I've defined it, I do have to say parameter 0, that's the float 4 itself, is filled in this way with a slightly better implementation. The 0 float 4 thing and these curly braces would be redundant, and the code would be a little bit cleaner. Unfortunately, because the CUDA float 4 is a wrapper around a float 4, this is a tiny penalty, I guess. Penalty in terms of how not nice it looks, but doesn't really have any serious impact on how the code works, just doesn't look as nice. And the same for float 3. We'll do the same thing here over and over again, and again, this could be improved eventually to get rid of this extra 0 float 3 and the curly braces, which would make it a little more compact. Okay. Back over here, so points and acceleration, here are our device buffers. We're going to take them, and we will then get ready to send them in. Here's what we'll do. We have our unsafe block, we have our result, and we call launch with module.calculateForces, and for our arguments, we say there are num points, chunks of work, that is 100,000. Each chunk has one thread. If you don't get this right, by the way, the code doesn't work as expected. If you put 1 and 1 for both of these values, then only the first acceleration has been calculated, because we said there's one chunk of work and there's one thread, but actually that's not sufficient. Nothing's fancy for shared memory, and then the stream that we saw earlier, and then we provide our arguments, which have to match with the expectation of the kernel. So our points are accelerations, and then we also have to add the number of points, so our iterations are correct. That's it. And then we have an extra here, result question mark, which just says, look, if result didn't work as we expected, if something is wrong, we want to show the error here instead of ignoring it and trying to go on further. Then we synchronize. Then we copy the results back to host memory. So we've got them in the device buffer, and our goal is to just move them back into the original accelerations vector. And then we can print our accelerations, and that's the ball game. Then we're done. That's how we actually execute it. All right, the walkthrough of that code is pretty quick because there's not too much new to see there. It resembles to a great degree the original of the launching a simpler kernel combined with something that we already saw and already know, and therefore there isn't a lot that I could break it down without repeating myself a lot. Here's what you actually want to know, though. How much does it speed it up? So I ran this on ECE Tesla 1. The previous evaluations of, say, the n-body problem and n-body parallel and n-body with approximations and what have you, I did those all on my laptop, and it is a reasonable comparison. However, because I don't have the NVIDIA GPU in said laptop, I can't really make this an apples-to-apples comparison without rerunning the other programs. Therefore I have to rerun them on ECE Tesla 1. And so with 100,000 points, the sequential version with no approximations, all these are without approximations because I didn't write an approximations version of the CUDA kernel, so we can't, again, have an apples-to-apples comparison. But all of the 100,000 points without approximations for the original N-body in the sequential version takes 40 seconds. The N-body parallel 5.3 seconds, and the N-body CUDA, so parallel version with no approximations, takes 9.5 seconds. Now wait a minute, you were the chosen one. This is worse than the parallel CPU version. That's not what we were expecting. Okay, what's wrong here? Why is the CUDA version somehow worse? I'll give you a hint. It's... Well, my first theory was incorrect. So whatever your first theory is, you may be correct, you may be incorrect, but certainly mine was not correct. My first theory was that 100,000 points is not enough to overcome the overhead of setup and transferring data to and from the device. And Kylo Ren is very memeable, so more points. More. This turned out to be incorrect, and it was actually kind of painful to try the sequential version with 500,000 points, because you end up waiting quite a long time. I mean, it's not a huge deal in the grand scheme of things. If it takes 5 times as long, 5 times 40 seconds, it's only a few minutes, but still, it's not that nice when you're staring at it and seeing, did it get better or not. But that isn't correct. Or, if you want a sequel meme, for once, amazing. Every word of what you've just said is wrong. I looked into it, and what I did is I brought out the profiler, and I keep telling you we're going to talk about profiling, and we will as soon as we're done with the GPU type discussion. And the profiler told me that most of the time was going to the kernel execution of calculate forces. So it wasn't that we were losing a huge amount of time in the overhead, where you'd see, 80% of your time is going to overhead, and only 20% is going to calculate forces, and that's why. And eventually, if you just keep cranking up the problem size, you will eventually end up with a better outcome. No. The time was going to kernel execution of the data, which is to say where it should be, where it's supposed to be, which means something else is wrong. I don't think there's really anything terrible about the kernel itself, but here's what I thought about, and this one turned out to be correct, and I apologize for the really not great quality of this diagram. It's one from the NVIDIA documents, and it's really not good, but whatever. The documentation on grid and block size is very unclear. I would say it's not super specific about what these values should be, or how to choose them, or what impact it has, if any. And for that reason, if I just said, look, there are 100,000 work items, each of size 1, I get, not very good performance. So by revisiting this and thinking about it, and also consulting with Google, Google's... it takes you to a number of sites where it says, experiment and try. I mean, here's the thing. That's not specific enough to be really actionable. Trying random values and seeing if we can zero in on some better outcome is a last resort. I would like to make some intelligent decision and see if it improves things, and not just make a random change. I don't want to go about it that way, because we could be at it for a very long time. Anyway... What I've discovered is that having each work item be its own grid is effectively what would happen, and that's inefficient because we're not taking advantage of all of the hardware that's available in the warp. The advice that I can find says the number of threads per block should always be a multiple of 32, with a maximum of 512 or maybe 1024 with more modern devices. And the other guidance I find is basically try something like 256 or 128. If that makes it a lot better, good. If you need to adjust it a little more, you can always adjust it a little more. Try something else, and go from there. That's I mean, it's more helpful than it would have been, but is otherwise, still a lot of guessing when it could be. It could be explained a little bit better. All right, so here's what I did. I took 256, and then you have to adjust the grid size, right? So I have to divide the number of points by the threads per block to give the correct number of grids. And I also have to add +1 to that number of grids because 100,000 does not divide evenly by 256. If you leave that off, then the last block, however many are left over, end up getting kind of forgotten, and their accelerations are all 0, and you're looking at that and you're saying it's right most of the time, but why not here? So the only things I changed are inside the angle brackets on the first part of the launch macro. And what I said is num points divided by 256 plus 1. That's the number of work items to do. And then to that, I have also said there's 256 items to do in each work item. And that's it. Did that solve the problem? Well, no. Nope. I forgot something else. It led to the kernel crashing. Why? Well, the answer is because the indexing strategy that I used contained only a reference to the block index.x. That's fine in a scenario where every work item gets its own block, but it is no longer the case now. 256 work items share each block. So to be a bit more explicit about what I actually changed in the kernel, it's of course better if I show you. And in the course repository, the nbody CUDA grid project is the one where I have the changes applied. You can see that here in the launch macro call, where it's calculate forces with num points divided by 256 plus 1 with 256 items per grid, and so on. But actually, the other thing to change is in the kernel. And the only real change here is on line 22, where I do a better calculation of the actual index for the position that we are looking at here in our grid. So it's the thread index plus the block index times the block dimension, which then successfully calculates the correct offset. If I just use the block index.x, then it doesn't work because we're failing to account for the size of the block as well as which thread within that block we are using. And by doing the multiplication and the addition, we end up calculating the correct index, and then we can use that index to get the position that we are interested in, the acceleration, and then assign it back when we are done. Everything else in here is the same, and so you can see that the difference between the code that works well and the code that doesn't work well is very tiny. This calls back to one of the things we talked about in the laws of performance software, in that does this version work better? I mean, take my word for it, it does, and I'll show you how much better in a minute. But the change is very small. Here I changed one line, and in fact I just changed these numbers. Okay. And here, where in the previous code I just used blockindex.x everywhere, but if I had extracted it to its own variable like this, I would have just changed this line only, and we'll see how much of a difference it makes in our actual performance. Hint, it's a lot. All right, and now we're back to prequel memes, as all things should be. And I reproduced here the versions that we saw before. So 40.3 seconds for the sequential version, 5.3 seconds for the parallel version, and the CUDA version 9.5 seconds without using the correct grid size, and with the correct grid size 1.65 seconds. So that's a lot better. We are finally putting the parallel compute power of the GPU to good use here. We are taking much better advantage of its capabilities, and as a result of that, we are getting a much bigger speed up, and we can see that even with 100,000 points, it's actually worth doing with the GPU. Again, I've measured the timing here with Hyperfine, so we've done several runs, and it's about the whole program runtime, but we have, again, previously established that generating the random points and putting them in the vectors and what have you, that is very fast. The slow part is actually in the calculation of forces, and by offloading that very parallelizable problem to the GPU, we have sped up the observed wall clock runtime of our program execution by quite a lot. This may lead you to have some questions about like what kinds of things can we do with this newfound power that we have, and that is a topic that we will cover just coming up next.